Hey guys, welcome to lecture number 23. So in this lecture, we'll be talking about what I would say the most important theorem in the entire calculus course. And this is what we call the fundamental theorem of calculus. We'll see a bunch of applications. You will see how to compute the derivative of a function which is given by the antiderivative. And also, in the second part of the lecture, I would like to dwell more on how to compute integrals using substitution. All right, so let's get started. So I would like to start with the fundamental theorem of calculus, and I'll just dive directly into the subject. So the first part will be talking about the fundamental theorem of calculus. All right. Okay, so this is, we'll be talking about this in the first part, and we'll see, like I said, a bunch of applications. And let me just say it directly. So we have the following theorem, which basically says the following. So if f is defined on a closed interval AB is a continuous function, and f, so capital F, is any function that satisfies f prime of x equals f of x, so is the antiderivative, right? Throughout this interval, then we say that the following formula holds true. And this formula, I'm going to write it like this. So it's the integral from a to b of f of x dx will be nothing else than just, I'm going to write it like this, the antiderivative f of x from a to b. And this will be nothing else than just f of b, so f evaluated at the point b minus f evaluated at a. So this is the most important formula in the entire course. As you can see, when we have this integral, this is f of b minus f of a is nothing else than just a number, right? So we can say this. I want you to look at it. This is a very important formula. Like I said, it will be very important when we evaluate integrals. And let me just start with an easy example. In fact, I want to go back to the example that we did last time. Remember in the previous lecture, we did this example of evaluating this integral. And I told you that we're going to do it the hard way. So evaluate this integral from -2 to 1 of 4x dx. And the way we did this through Riemann sums, and then we computed them and so on, and we passed the limit as n approaches infinity. Oh my God, it was quite, I told you, it's that's going to be the first and the only time when I will solve an integral like this. Well, now with this tool in our hand, then we can compute this integral like really fast. Also, this is what we call, in fact, I would like to make a comment here. This is what we call also Leibniz Newton's formula. So it's due to these two mathematicians and physicists, Leibniz and Newton. If you're wondering about Newton, yeah, that's right, that's Isaac Newton, the one and only. All right, now let's evaluate this. So, and what we're going to do, so we have, so this integral from -2 to 1 of 4x dx is now, by applying the properties of the constant rule, multiple rule, we're going to take out the constant 4. So this would be 4 times the integral from -2 to 1 of x dx. And now this would be 4 times. And now we want to apply, so here we're going to apply the fundamental theorem of calculus. Right? And at some point, I will abbreviate this by FTC. You will understand when I put here FTC, this is nothing else than just the fundamental theorem of calculus. All right. Let me write it here as well. The fundamental theorem of calculus. And now, if we look here, so this would be, what is the antiderivative of x? So the antiderivative of x is x squared over 2 from -2 to 1. And this would be equal to 4 times, and let me put it like this, 1 squared over 2 minus, and we should be careful now, -2 squared, -2 over 2 squared. And this would be equal to 4 times, this is 1/4 minus, this will be -1 squared, which is 1. 1/4 minus 1. And this would be 1 minus oh, wait. So this is 1 squared. Okay, I think I made a mistake. Jesus Christ. Okay. Give me 1 second. It was a silly one. So this would be -2 squared over 2. And this would be equal to, at the end, we'll have 4 times 1/2 minus 4 over 2, which is 2. And this would be 2 minus 8, which is -6. Okay, so that's exactly the answer that we got. You see, there is a very simple way of computing integrals, right? And in this case, let me give you a bit of an explanation. Keep in mind that the antiderivative, so remark, the antiderivative of the function, let's say f of x equals x, is capital F of x is x squared over 2, right? Because capital F prime of x is f of x, right? So that's, all right. Now, let me point out another remark. So this is 1, 2. Also notice that in the definite integral, so in the definite integral, because one of you might ask now, what happened to that constant? Remember that when we computed the indefinite integral, if you look at the fundamental theorem of calculus, of this formula, you'll look and you'll see that what happened to that constant? Well, we don't need that constant. When we deal with a definite integral, there's just a number. But when we have an indefinite integral, we'll have that the antiderivative plus c. So in this case, so in the case of the definite integral, we can ignore the arbitrary constant c, right? We can ignore that because the solution does not depend on C. Does not depend on that constant C. So in other words, we have, you see, in the case of indefinite integral, we had that the integral of f of x dx was the antiderivative f of x plus the constant C. And in the case of the antiderivative, we will have the integral from a to b of f of x dx is nothing else than just, if we want to write it in using the above formula, so it will be f of x plus c, and then we're going to take everything here from a to b. But now if we, this would be nothing else than just f of b plus the constant c minus f of a plus c. And then guess what? This will be nothing else than just f of b plus c minus f of a minus c. Oops, minus c. And the constant will just go away. So this would be nothing else than just f of b minus f of a. Right? So this is what you have to keep in mind, that the integral from a to b of f of s dx is nothing else than just the antiderivative evaluated at b minus the antiderivative evaluated at a. All right, now let's see some other examples. So exercise, let's say exercise 1. So now we're going to do many examples of the fundamental theorem of calculus, and the way I'm going to interpret this is will be in the following way. So find the area, let's see, under the curve, and let's just take a curve. Let's say y equals cosine of x, and let's just pick an interval on negative pi over 2, pi over 2. All right. So the area under the curve, as you already know what this means, is the nothing else than just the integral. So we have that the integral from negative pi over 2 to pi over 2 of f of x dx, which in our case will be the integral from negative pi over 2 to pi over 2 of cosine of x dx. And this would be, we're looking for the antiderivative of a cosine of x, which is nothing else than sine of x, from negative pi over 2 to pi over 2. And this would be sine, by the fundamental theorem of calculus, this is sine of pi over 2 minus sine evaluated at negative pi over 2. And this would be nothing else than just 1 minus, and this would be negative 1 minus negative 1, which is 2. And that's the answer we're looking for. Right? Now, let me draw a graph so that you can see the area. So let me just draw it here. So let's just say here we have negative pi over 2. Let's just say here we have pi over 2. So it's going to go like this. Well, it doesn't look quite simple anyway. So this is, let's just say that this is the graph of y equals cosine of x. So the area under the graph, you see this area here, right? This guy here. So the area under this graph, this is nothing else than, oops, so this guy here, this guy is nothing else than just this integral. So this is the integral from negative pi over 2 to pi over 2 of cosine of x dx, right? And this is nothing else, the area is 2. All right. Let me see another one. So this is the first one. Now let's see another example. So exercise 2. Again, we want to find the integral from negative 3 to 5 of negative 10 dx. pay attention here because it's a little bit of a trap. It's just a constant. So here, this integral will be nothing else than just, so the integral from -3 to 5 of -10 dx will be, so we're going to take the constant now, so it will be -10 times the integral from -3 to 5 of dx. And here we have 1 dx. And now this will be -10 times. And now look at this. So this will be, what is the antiderivative of 1? So the antiderivative of 1 is x from -3 to 5. So this would be nothing else than just -10 times 5 minus -3. And this would be -10 times 5 plus 3. And this would be -80. And that's the answer. Anyway, we can draw a graph here as well, but I will leave it this to you as an exercise to figure it out how to. Anyway, now let's see another example. Let me see. Now let's evaluate a little bit more of a complicated function. So we want to find the integral from 4 to 9 of 1 over square root of x plus x dx. So what is the value of this? As you can see, we have inside the integral, we have the sum of two functions, right? So in this case, we have that the integral from 4 to 9 of 1 over square root of x plus x dx is, by applying the sum rule, this is the integral from 4 to 9 of 1 over square root of x dx plus the integral from 4 to 9 of x dx, right? And this would be equal to, and now we have to compute each integral. So in the first case, this would be, so this is equal to, let me write it in this way. So for the integral from 4 to 9 of x to the -1/2 dx. So I can write it like this, plus the integral from 4 to 9 of x dx. Okay, so now we have power functions on both sides. So this would be x to the -1/2 plus 1 over -1/2 plus 1. And now we should be careful here, from 4 to 9 plus the antiderivative of x is x squared over 2 from 4 to 9, right? And this would be equal to, and now let's do some computation. So this would be -1/2 to a -1/2 from 4 to 9 plus x squared over 2 from 4 to 9. All right, so this would be, if we look, right? So this would be what? Well, this would be x to x to the 1/2 would be, okay, so this would be 2 times so we have 2, okay, 2 times x to the 1/2 from 4 to 9 plus 1/2 x squared from 4 to 9. And anyway, now we plug, once we plug in, we'll have 2 times 9 to the 1/2, so it's a square root of 9, which is 3 minus 2 plus 1/2. Here we have 81 minus 64, minus 16, sorry. And this would be equal to, well, 2 plus 1/2 times 65. Oh, and this would be 69/2. And that's the answer. Anyway, so it was a little bit more involved, but not that complicated. But now let's evaluate another function. So exercise 4. Now let's evaluate, so find, and now let's just take something with the absolute value. So let's just take the integral from -2 to 2 of the absolute value of x dx. So we want to find this integral. All right. Well, unfortunately, we don't know the antiderivative of the absolute value of x. So what we need to do is to write a definition of the absolute value. So we know that the absolute value of x is positive x if, if x is strictly greater than 0. And let's just say negative x if x is less than 0. And of course, 0 if it's 0. So we know that. All right. So let me just draw a graph of the absolute value, because we can draw the graph of the absolute value and you will see why something amazing happens to the integral. So let's just say, so it's defined from -2 to 2. And the absolute value of the graph goes like this. Right, these two are perpendicular lines. So this is the positive part, y equals x, and this is the, let's say, negative part, y equals -x, right? And we're asked to compute this area, basically. Well, it should have been symmetric, but it's not. But anyway, you can imagine this, even though the picture is not the greatest. So, well, okay, let me draw to be more exact. Because I want the picture to look good. And I want -2 to be, okay, to be here. Okay, the graph keeps going. Oh, okay, these two are perpendicular and it will go like this. And now at this point, okay. All right, now at this point, they look kind of similar. Right, as you see, they're symmetric, and you can guess that that something happens to the area. Well, it's quite clear to figure out how much the area is by just looking at the two right-angled triangles, if you want, and you can compute the areas. But anyway, let's do it. So this part here is nothing else than just the integral from 0. So this is 0 here, from 0 to 2 of x dx. And this part here is nothing else than the integral from -2 to 0 of -x dx. Right? So that's what you need to know. All right, great. Now we can write the integral. So let's do it. So the integral from -2 to 2 of the absolute value of x dx will be nothing else than the integral from -2 to 0 of -x dx plus the integral from 0 to 2 of x dx. And this would be, so this is what we call the subdivision rule we applied here. So this would be equal to, let me write it this way. So here we apply the subdivision rule. In fact, let me do it like this. So here we apply the subdivision rule, right? And now we can compute each integral, and you know, this would be negative. Let's take the negative out of this. And this would be the antiderivative of x will be x squared over 2 from negative 2 to 0 plus, again, the antiderivative of x will be x squared over 2 from 0 to 2. And this would be equal further on. This would be, so like I said, we apply the fundamental theorem of calculus here. And this would give us negative, so this would be 0 over 2 minus negative 2 squared over 2, right? Plus 4 over 2 minus 0 over 2, 0 squared over 2, anyway. And this would be equal to, again, it's just the computations. This would be, let's see, so 4 minus 2 plus 2 minus 2, so this is negative. So this will be 2 plus 2, which is 4. Well, it's quite clear if you look at the area. So the result should be 4 because the area of this of the first right angle triangle is 2. The area of the second right angle triangle, as you can imagine, is again 2. So there you go. All right. This is how we compute when integrals when we have the absolute value. Now, let me tell you something. So I gave you the first fundamental theorem of calculus. Now, let me give you the second fundamental theorem of calculus. So, theorem, and let's just call this the second fundamental theorem of calculus. Okay. And the statement goes something along these lines. So let's consider that f of t, right, be continuous. So we're going to consider, again, a continuous function on the interval. So on interval AB, right? And define the function so we're going to define the following function, g, capital G, by the following integral equation, let's say, by the integral equation. And let me write it in this way. So the integral equation is g of x is the integral from a to x of f of t dt. Right? So, okay. Then, guess what happens? Then, g prime of x, well, as you can see now, this would be, let me write it slowly, will be what? Will be, by the fundamental theorem of calculus, this would be f of x minus f of a prime. In fact, let me write it in this way. Would be the integral from a to x of f of t dt, everything prime. So this would be nothing else than just f of x minus f of a prime, where f of x is the antiderivative, or the capital F of x is the antiderivative of f. So this would be nothing else than just the f prime of x minus f prime of a, right? But f prime of a, f of a is a constant, so f prime of a will be 0. So this guy here, it's 0. And this would be f capital F prime of x, which is f of x, because the antiderivative is nothing else than just f of x. And now let's see an example So this is how we compute. Basically, it's just an application of the, I would not call it the second fundamental theorem of calculus. I would just say that it is an application of the fundamental theorem of calculus, the one and only. But anyway, let's call it like this. And let me give you an example. We'll do a bunch of examples. So the first example that I have in mind is the following. Let's say g of x is the integral from 2 to x of t squared dt. Right? And now what we would like to do is just to compute g prime of x. Well, we can actually say who this is, but anyway, let's identify the function inside. So in this case, so f of t is t squared, right? So the integral, so g of x, which is the integral from 2 to x of f of t dt, will be nothing else than by the fundamental theorem of calculus. So here you just apply the fundamental theorem of calculus. So this would be f of x minus f of 2. Where f of x is the antiderivative of this. So this would be, the antiderivative will be, in fact, yes, so it will be what? So it will be t cubed over 2, right? Replaced by, so, okay, let me do it like this. So let me write it here. F of t will be t cubed over 3. So this would be x cubed over 3 minus 2 cubed over 3. So this would be x cubed minus 8 over 3. Okay, so this is who g of x is. Look here. And now, right, look at this here. And now I'd like to compute the derivative. Well, guess what? I can take the derivative of that if you want. So g prime of x is nothing else than just x cubed minus 8 over 3 prime. This would be so this is 3x squared minus 0, minus nothing. So it will be x squared, which will be, well, as you can see, if we go back with what we did, look, we identify here g prime of x. This is nothing else than just f of x. The function is inside. You see, the function inside here is t squared. So in our case, I got exactly x squared. You see? So it's just an application of the fundamental theorem of calculus. All right, now let's see another example. So example 2, we'll do a bunch of examples. Now let's consider let f of x to be the integral from 7 to x of 2t minus 3 dt. Again, find f prime of x. Let's see, maybe it is the function inside. Maybe it's 2x minus 3. Or maybe not. We'll see. We should be careful here. All right, so because we have the difference of two functions here. All right, now let's write this. So you see, we can split this integral. So f of x is the integral from 7 to x of 2t dt minus the integral from 7 to x of 3 dt. And this would be equal to, oh, sorry about that. So this would be equal to, so let's take the 2 outside. So this would be the integral from 7 to x of t dt minus 3, the integral from 7 to x of dt. And now by applying the fundamental theorem of calculus, I'm going to say here, this would be equal to 2 times t squared over 2 from 2 to x minus 3 times t from 7 to x, not 2, geez. And this would give us 2 times x squared over 2 minus 7 squared over 2 minus 3 times x minus 7. And now we can just do the computations here. And once we do the computations, this would give us what? Well, x squared minus 49. Okay, so it's x squared minus 49 minus 3x plus 21. So this would be x squared minus 3x plus minus 28. So that's the function, that's f of x. But pay attention, we're interested to find the derivative. So f prime of x will be nothing else than just x squared minus 3x minus 28, everything prime, which is 2x minus 3. Wow. Guess what? Look at this guy inside here. Oh, wow, maybe it's the same. You just have to replace t by x. But pay attention, there is a trap here. You're lucky because one of the limits of the integral is a constant. You will see what happens when one of them is not a constant. But anyway, we'll get to that. Let me do another example. Again, let me consider example 3. So let's say f of x to be the integral from 0 to x squared this time of t squared dt. Again, find f prime of x. All right. All right, let's do it. Well, again, we have that f of x will be nothing else than just, if we know the antiderivative of, again, let's say f of t is t squared here, the function inside. So f of x will be t cubed. All right, let me write it again. So f of x, which is the integral from 0 to x squared of t squared dt, will be nothing else than just t cubed over 3, which is the antiderivative of t squared from 0 to x squared. And this would be, if we look, 1/3 times x to the 6th minus 0 cubed. So this would be 1/3 x to the 6th. All right, so f prime of x will be 1/3 times x to the 6th prime, which is 1/3 times 6 x to the 5th, which is 2 times x to the 5th. Wow, look, you see, now we have something here. Look at this guy. And here, this guy is not the same. You see, this is what happens when you have, instead of x, you have x squared. So pay attention. Don't fall into this trap. When you have the one of the bounds is not x anymore, and is not a, when you have a constant, let's say 5 or 0 or whatever, and the other bound is x, then yes, everything works just fine. But when you don't have x and you have an x squared, then the situation will get a little bit more complicated. Well, stay tuned, don't go away, because we'll have more complicated examples than this, right? So, and now I'll discuss some of them, in fact, in the, yeah, I should discuss some of them at the review session. And now I would like to veer towards the second part of this lecture, which will be devoted to the integration by substitution. So the second part, integration by substitution. All right, so the theorem is the following. Let me consider let f and g be two and u. We're going to consider three functions, in fact, f, g, and u be differentiable functions right, of variable x such that we can say that such that f of x is nothing else than just g of u times du over dx, right? So we take the derivative of u with respect to x. And then we have the following formula. And the formula is the following. I'm going to write it like this. The integral of f of x dx will be nothing else than the integral of g of u du dx, right? Which is nothing else than the integral of gu du. So we have the new variable now. So instead of x, I have u, and we call this the u-sub, the u-substitution. So this is the formula, right? And now I wrote this for the undefinite integrals because I would like you to see how it looks like. And we're going to operate with some undefinite integrals at first, and then we'll see some other definite integrals. And basically, it's just the same. So I want you to have a very good look at it. This is a very important formula. I know. Let me do. Let's do a couple of examples. For example, here's say example 1. So also keep in mind that we have this guy here. All right. So I think the statement is a little bit. It's much more confusing than the actual applications. You'll see in applications that. It's much easier than you think. For example, let's say find, let's say, make f of x. So we find this integral. The integral, I'm going to take an undefinite integral of 9 times, let's say, x squared plus 3x plus 5 to the power 8th times 2x plus 3 dx. Okay, look at this integral, and there is something that you will see here. So what is that thing that you observe? You see, if we look at this quantity here inside, if we look at this guy here, well, if you take the derivative of that, you'll find exactly this guy here, right? So x prime, let me point out. So observe that x squared plus 3x plus 5 prime is nothing else than just 2x plus 3. Okay, so with this observation in mind, now as you can see, we can perform the u-substitution. So I'm going to write it. So we're going to say let u be this guy, x squared plus 3x plus 5, right? And it follows that du, so if we take the differential, this would be dx squared plus 3x plus 5, and this would be nothing else than just, if you want, 2x plus 3 dx, right? So du over dx is, so du over dx is 2x plus 3. Or like I said, you can write du equals 2x plus 3 times dx. Or dx will be, if you want, du over 2x plus 3. All right, great. And now we're gonna, you see, we'll replace this. So f of x will be the integral of 9u to the power 8th right? And now dx, 2x plus 3 dx will be, so will be du, right? Wait. Oh, okay, so it's 2x plus 3 plus times du over, yes, I forgot about this 2x plus 3 over 2x plus 3, right? Okay, so this would be nothing else than just the integral of 9 u to the power 8 du. So this would be 9 times the integral of u to the power 8 du. And this would be equal to what? 9 times u to the power 9 over 9 plus constant, right? So this would be u to the 9 plus constant. So this is where c is an arbitrary constant. And now we go back to the substitution. Pay attention, because we are asked to find everything in terms of x. So finally, f of x will be nothing else than just, well, let's look where is our substitution, u sub, look at it, it's right here. So f of x will be nothing else than just x squared plus 3x plus 5, everything to power 9th plus c, and we're done. And this is the antiderivative, this guy here. Okay. Now let's do another problem. Example 2. Is to find the integral from 2x plus 7 to the power 5th dx. And now, well, it's quite clear that because it's not productive for us to expand, to raise everything to the power of 5. God, that would be a mess. Usually, if, for example, if you had instead of 5, if you had like 2, you would be tempted to square that, and then you just compute each integral. But here we have power 5. It's very unproductive to raise everything to the power of 5. So what we're going to do, we're going to consider a substitution, maybe u equals 2x plus 7. So this would be, from here, du is the same as 2 dx, right? So this integral from 2x plus 7, everything to the power 5th dx, will be nothing else than just the integral of u to the 5th. And now dx is 1 over 2 du, so it's du over 2, which will be 1/2 the integral from u to the 5th du. So this is nothing else than just 1/2 times u to the 6 over 6 plus constant. And this would be nothing else than just u to the 6th over 12 plus constant. So this would be nothing else than just 2x plus 7 to the power of 6 over 12 plus constant. And again, this c, where c is an arbitrary constant. All right, now let's see another example. Example 3. The integral of cosine of theta, let's just say sine of theta d theta. Let me see if I pick the right integral. Okay. Now it's quite clear what the u sub should be, so we need to find this. Now let u to be 4 minus 2 cosine of theta. So du will be nothing else than just 2 sine theta d theta. So du over v theta is nothing else than just 2 sine of theta. Okay? Or if you want, now our integral, the integral from 4 minus 2 cosine of theta cubed sine of theta v theta is nothing else. Now it's going to be the integral of, so now we're going to, this will be u cubed times sine of theta d theta is nothing else than just du over 2. So the constant will take it outside the integral. So this would be the integral of u cubed du. So this would be nothing else than just 1/2. And this would be u to the 4th over 4 plus constant. So it's u to the 4th over 8 plus constant, where c again is constant, is an arbitrary constant. Right? Now let's see another example. Example 4. Let's see. Find let's say the integral of x times e to the 4 minus x squared dx. Again, we're gonna do the following u sub. So let u be 4 minus x squared. So this implies that du is negative 2x dx. So our integral, let's just say that the integral of x times e to the 4 minus x dx is equal to, x is, let me just write the integral of e to the u times x would be, so x dx is negative 2 du, over 2, negative du over 2, sorry. And this would be nothing else than just negative 1/2 the integral of e to the power u du. And this would be negative 1/2 plus times, e to the u plus c. And right, where And if we go back to the substitution, this would be nothing else than just -1/2 times e to the power 4 minus x squared plus constant c, where c is a constant. Right. All right, there are some other examples in my notes, and I'm going to leave this to you before I. So another example, example 5. I'm just going to tell you the main idea. So we want to find the, let's just call it in the following way. So this is f of t is the integral of the square root of 3t plus 1 dt. As you can see in this case, we have the integral of a square root. So maybe inside the square root we have a linear function. So maybe it's not convenient for us to just do some tricky things with the square root, not yet, but perhaps the idea, let me just give you the idea. So the main idea is to do the following substitution. U is 3t plus 1, and so on, etc. So you take du is 3 times dt, and then you have the integral of the square root of u, and then this is the integral of u to the 1/2, and you know how to compute that and so on. Anyway, I'll leave this to you as an exercise. Now I want to veer towards because we've dealt only with indefinite integrals. Now I want to deal with definite integrals. So substitution. So this will be the substitution with definite integral. All right, the theorem states the following. So if f of u is a continuous function of u, and u of x is a differentiable function of x, then the following formula holds true. And let me write it in this way. So this is the integral from a to b of f of u of x times u prime of x dx, right? This will be the integral from u of a to u of b of f of u du. So this is how we write the change of variables formula, if you want. For definite integrals. So let me box this. And we will use this formula. I want you to look at it. Okay. All right, now let's see some examples of this. Let's some applications. Let's see example 1. First example that I have in mind. So this time we will compute only definite integrals. So the first one, let's pick something easy. So evaluate this integral. Let's just say from 1 to 2 of 4x minus 5 everything cubed dx. Right. So let's see. So how are we going to evaluate this? You see, again, we have this function 4x minus 5, everything cubed. Of course, I can raise everything to the power 3, and I can do all these computations and so on, but you know, I don't want to do a lot of calculations now. Definitely don't have time for that. So maybe we should do something smart. And again, this u sub comes to the rescue. So this would be, let u be 4x minus 5, right? So here we have that du is 4 dx. So our integral, we should be careful now. So dx is du over 4. Okay, let's write it like this. All right. And now pay attention because we need to update the limits of the integral. And we're going to do it in the following way. When x is 1, u is what? Is 4 times 1 minus 5, which is negative 1. And when x is 2, u will be what? 4 times 2 minus 5, which is 3. Okay, so our integral, so now we're going to rewrite the integral in terms of u. So we're going to have the following. So we have that the integral from 1 to 2 of 4x minus 5 cubed, everything cubed, dx, this would be nothing else than just the integral. Now this time the bounds are, as you can see here, are negative 1 and 3. So this would be the integral from negative 1 to 3 of u cubed. And now dx will be, look at this guy here, right? So this would be du over 4. And we're going to take 1/4 outside. So this would be the integral from negative 1 to 3 of u cubed du. And this would be 1/4 times, and now the antiderivative of this will be u to the 4th over 4 over negative 1, from negative 1 to 3. And now we're just going to do some computations here. So this would be 1/4 times, in fact, 1/16. Sorry about that. 1 over 16 times u to the 4th from negative 1 to 3. So this would be 1/16. 1 over 16. 81 minus 1. So it's 80 over 16. And that's the result. Wait. Yeah, which is 5. Correct. Yeah, this is 5. And that's the final result. Right? So that was a simple one. Now let's do another one. Maybe a little bit more complicated. I like to do a much more complicated, I won't say much more, but more complicated examples. So example 2. Maybe I'll do two more examples. All right, so here we want to evaluate the following integral. So evaluate the integral, let's say the integral from 0 to 1 of x squared and x cubed plus 9, everything to the power 1/2 dx. Well, you can say the square root, but anyway, you can leave it like this. It's fine. Okay, let's look at it. So what kind of approach should we use here? You see, you have complicated, well, you have complicated functions inside that the square root, not so complicated outside the square root. So you have x squared, which is nice, but also x cubed plus 9 is also a nice function. But you have the square root, so you cannot operate with the square root that easily, especially when you have something x squared plus x cubed plus 9, everything to the 1/2. And of course, there is no such formula to raise to the power 1/2. Well, not something that you are aware of. So we should do something about it. So what should we do? Well, guess what? If you look at the integral closely, you will observe that there is a relationship between this guy here and this guy inside. You see, and they're almost the same. Well, if you take the derivative of x cubed plus 9, you will find that this is almost x squared. Well, you have a constant 3 there. So maybe we should do this u sub. So let's see. So let u be x cubed plus 9. So once we have this x cubed plus 9, it follows that du is nothing else than 3x squared dx. So this means that, let's write it like this, that du over 3 is equal to x squared dx. So our integral from 0 to, and I would like to point out something before we start changing the variable. First thing, we need to change the limits of the integral. So when x is 0, u is what? Is 9, right? When x is 1, it follows that u is 10. So our integral will become the following. So the integral from 0 to 1 of x squared times x cubed plus 9, everything to the power 1/2 dx. This would be nothing else. Then now we're going to change the limits of the integral. So pay attention. So now the limits will become 9 and 10. So this would be the integral from 9 to 10 of x squared dx will be so it will be the square root. So it will be what? U to the power 1/2 times, and now x squared dx, it will be nothing else. If you look here, is nothing else du over 3. So this would be du over 3, which will be 1/3 times the integral from 9 to 10 of u to 1/2 du times. All right, and now we have to compute this. So this would be u to the power 1/2 plus 1 over 1/2 plus 1 from 9 to 10. Oh my. And now we're going to do some computations. Oh, so this would be, let's do more algebra. 1/3 u to 3/2 over 3/2, or from 9 to 10. And this would be 2 over 9 times u to the 3/2 from 9 to 10. So this would be equal to what? 2 over 9 times 10 to the power 3/2 minus 9 to 3/2. And this is nothing else, 2 over 9, 10 to 3/2 minus, this guy will be 27. Okay, and that's the result. I'm just going to leave it like this. Anyway, it doesn't matter. So this was a little bit more complicated than the others, but not so much. And now let me just do one more, and after this, probably I'm gonna stop. It's already late by now. So the example number 3, and that's it. Again, evaluate this integral from 0 to 1 of e to the x over 1 plus e to the x dx. Okay. So now, as you can see, we have the quotient of two functions, which involve the exponential, but it's maybe we should just do a notation or a substitution. Maybe we can take, we have two options though here. You either take e to the x equals u, or you substitute 1 plus e to the x equals u. Let's just do the other so that we can get rid of the constant 1 as well. So let u equals 1 plus e to the x. And from here, it will imply that du is e to the x dx, right? And now, let's see. When x equals 0, so we're going to change the limits of the integral. So this will be when x equals 0, u is u plus e to the 0, so it's 2. And when x is 1, this will imply that u is 1 plus e. Okay, that's great. So our integral will become the following. The integral from 0 to 1 of e to the x over 1 plus e to the x dx will be nothing else than just, now we're going to change the bounds. So it will be from 2 to 1 plus e of, and now let's not forget what the u sub is. So it's here, right here. So this would be, so it's e to the x. So, okay, so so it will be du over u. So this would be, if you want, okay, let me write like this, the integral from 2 to 1 plus e, or 1 over u du, which is nothing else, pay attention, is the natural log of the absolute value of u from 2 to 1 plus e. And now, by the fundamental theorem of calculus, this would be ln of 1 plus e minus ln of 2. So this would be, if you want, ln of 1 plus e over 2. And that's the result. Right? I hope it's clear. Okay. I think this is, I'll stop here for this lecture. There will be another lecture. Well, I'll be, in fact, 2 more lectures, but I think for the final exam, this should be more than enough. The other lecture that I would like to point out was, it's again, a very important lecture when I will be talking about, well, something very important in calculus as well, which is called the mean value theorem for integrals. So this would be nothing else than just an analog of the classical mean value theorem for differentiable functions. And then at the end, maybe that's just a lecture, a recreation for you, because it's not usually done in Calculus 1. We'll be talking about numerical integral formulas. We'll call them the quadrature formulas. You'll experience more of these in when you take a numerical analysis course. But so far, we've done the essential for this chapter. All right, I think it's a good place for me to stop. Thank you very much.